and welcome you all to the last and third session of second day of the FDP on recent issues and challenges in AI and communication. So I'll be showing you some demonstration on a transformer-based classification model that uses MNIST dataset for classification purpose, and we'll try to cover the coding and demonstrate the results along with the model description. So let me share you my screen. Is it visible? Please respond someone. Okay, great. So after the session, I will also share with you the notebook files that you can use and replicate the results. And if yeah, thank you. So that after this session, you can build upon this work and develop your own model. Okay. So first thing first, we'll install the necessary libraries. I kept it simple for the illustration purpose. So we need to install the Torch Vision, and Matplotlib libraries. We all know Torch and Torch Vision will be required to design and develop our models, and Matplotlib for simple plotting, for curve plotting, which will be used for visualizing the results. And we'll import the required libraries. First, we install the necessary libraries, and then after that, we'll import whatever is required to develop our model. So for which we need torch.nn, which will be imported as nn. That stands for neural network, and torch.optim for selecting and using the optimizer, torch vision for vision related functions, and we need a transform function for transforming the images that will be described later. We'll also be using data, since the data have to be transformed in a manner that will be required for training the model. So we need the data loader function, which will be imported from torch.util.data, and obviously the matplotlib, in which the pyplot will be required, will be using to plot the results. So let me import these libraries as well. And the MNIST dataset. MNIST dataset is a collection of MNIST digit dataset is a collection of 0 to 9 digits that will be stored as images, right? So let me just show how these images will look like. So they are simply handwritten digits, and since the digits one can write in another way, and one may choose different writing skills. So it is a kind of tricky problem to convert this handwritten digits, or especially the image, into its number format. So it can be treated as one of the very basic problem of converting an image to text problem, like OCR, which the professional versions of the PDFs requires. So going back to loading this dataset. So as a practice, these datasets can be easily found with the links here, and we just need to import this. These are all also comes as package from in various packages of the various machine learning libraries such as TensorFlow or PyTorch. So we just need to provide the link, and the dataset will be downloaded. So torchvision.dataset.mnist. This will be the complete path of the MNIST dataset, and we will download this as a trained dataset and stored in the data folder. So on this data, the training will be done, means we have to mark the training as true, and we'll transform this data, and obviously we'll download. So the download will option will be true. For test data set, everything will be same. The training will be false, made false here. On this part, means test data set, we will perform only testing and not training, which will be required to evaluate how, after training, how good our model is performing. And then we build the data loaders on this. So train data set means that will be training part of the data set, which is taken into variable train data set, and will use a batch size of 64, and shuffling will be true. So what is shuffling is the data set which will be fed as data loader to the model for required training, that will not be contiguous, means continuous. One image may follow after any. So there is no proper sequence. Shuffling means shuffling is supposed to mean that only. And similarly, for test data set, shuffling may be true or false. It doesn't matter. So after importing the data set, we'll define our model. The model is easily defined. So let me go through the various module that will be required, and what is that. So for the final definition of the model, means Schwinn transformer, uh, with which we are using a channel attention as well. So for defining these model, this Schwinn transformer model, we need to define its various components like patch embedding, Schwinn block, channel attention, adaptive average pooling, and linear layer that will be imported and uh, imported and made as one component for Schwinn transformer. So for defining those, for use to be able to used with a Schwinn transformer, we define patch embedding. So many of you will be should be working with transformer, must know what patch embedding is. So if the image size is very large, so that might not be useful for direct training. So for that, we need to divide the images into various patches, right? And these patches have to be encoded uh, in number format, so that the similar, just as a case of NLP, where the similar words have to be are assigned a very similar coded value, encoded value. Just like that, the patch embedding means we are embedding the patches and assigning those codes, which means that similar image patches will have the similar embedding values. So patch embedding will do that only, and we have a simple convolution layer for that, and we need to project the input, and these then flatten and transpose into a linear combination of patches. Then we have MLP, that is multi-layer uh, perceptron. So perceptron, as we know, is very simple, just combination of linear layer with an activation function. So linear layer means linear layers means, suppose we have like these are neurons, and one may connect the layer I to I plus 1 like this. So MLP is made of this part only. And let me clean this. Okay. So and when the data or the feature maps, let's have some basic terminology clear here. So the input images first transformed into various patches. These patches are then assigned various code, uh, to using the patch embedding layers, and then these patches or these embedded patches, these embedded patches, is my voice clear? Okay, okay, okay. So then these patches, while feeding from one layer to another layer, there these are called feature maps, right? So uh, these feature maps are transformed layer by layer, and the where the attention is calculated, and based on attention score, and depending upon the problem, either we have a classification problem, then these patches have to be converted into, yeah, okay, have to be converted into probability vector of probabilities for a classification where the softmax can be applied, or the same setup can be repeated for any image restoration task, or image super resolution, or any similar image related task, right? Okay. So before we come to the swing transformer blocks, we have also used a channel attention mechanism in this model. So since the training will require some time, so let me start the training as well. For example, we have just used the 5 epochs, and since when the epoch will be running, I will be describing the model, saving us some precious time. Okay. So channel attention is what? It calculates the attention. Someone who is not familiar with attention mechanism, attention is something in context of images. We we see what other humans see, that some portion or some texture of the image attract our attention on the first look, means something different in the texture which differentiates it from the remaining background. So similar mechanism can be has been implemented through in various directions. Suppose XY, I mean we have plane XY, then it is called spatial attention. If it is implemented using depth wise, then or channel wise, then it is called channel attention. Some multi-scale channel attention strategies has been also implemented, and the multi-head attention also an extension of the spatial attention, right? So here we have used channel attention. So what it does is, it while take its input. Oh, okay. So since we have used the PyTorch implementation for the model, so one should be clear that defining a class, or in any implementation, will have a class name, then we'll have a constructor like init method, which will define only the various components that are to be used, right? Means only uh, creating the variable and the memory, that is something like that. And how the data, when how the data or feature map or any image when passed to this channel attention module, then how various transformation will be performed on the input data, that will be defined in the forward method. So forward method will take the self, means pointing this object, and an input x. Then upon x, what are the or what these components describe a mathematical transformation or any other transformation will be applied here. So we can see that average pool has been self dot average pool is a member of the channel attention class. It will accept uh, it has been assigned adaptive average pooling, right? Similarly, a max pool has been assigned adaptive max pooling. 2D means working with the images in 2 dimensional. Then an FC layer means fully connected layer. Just I described it will be a sequential layer consisting of a convolutional layer, which will use input channel and input channel upon reduction, means uh, how I mean by how much extent we are squeezing the channel information. Okay, and then we have a ReLU as an activation function, and again a convolution, and then sigmoid. These are pretty standard channel attention mechanism. You can also use a different combination of convolutional layers and activation functions to maybe develop your own attention mechanism or your own channel attention mechanism, which may be helpful in a particular application, right? So our channel attention component has been described here. And now see the when this input X right here, when this input X will be received as an input, as input, then 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 it will be passed to the average pooling function. And let's see, this is average dot fc. Yeah, and which uses nothing but self dot average pool. Let's see here. Self dot average pool has been described here, right? Okay. Again, uh, again average out, which will be output of the first line of forward method, will be placed in the next line, and no no the again the input X will be placed for max pool operation, and what we receive as max out, right? And this average output and max output added and multiplied with X. So one thing may be clear. This is the calculated value here is representing the attention score. Attention attention score, right? And when this attention score alpha, or maybe you may choose different notation while writing the manuscript, then this attention score multiplied with the initial feature map or initial image, maybe anything, image, text, or anything, right? Then we have a an image or a feature map that is multiplied with the attention score, and some of the features along with the channels. Means if the image have three channels RGB, then something enhancement will be done in the channel part, means RGB part, along the RGB direction, along the channels. Okay. Now we will define the swing block here. We will define the swing block here. So for different, I mean, as a default option, the embedding dimension has been chosen 64. MLP ratio has been chosen 5. So what is MLP ratio? As we described MLP. So it basically describes how dense your MLP means simple layer of perceptron, right? So how dense that layer is, okay? How dense that layer is is defined by MLP ratio, okay? And then again we'll have the members. Okay, so let me describe for someone who is not familiar with the swing transformer block. So swing transformer block actually uses the layer normalization first, okay, and then attention block. So the outputs first, the input is fed to the, let me say this X. Uh, yeah. The input X is first fed to the layer normalization block, and then that output of the layer normalization block will be fed into the attention block, and after this attention block, again the output is normalized, means again a layer normalization is added here, and after that the MLP layer is there. Okay. Now, usually this has the implementation is not like that, but usually we'll have a skip connection from here to here. and another skip connection from here to here. Means the output of the MLP will be added with the output of attention block. Okay, so attention mechanism or calculating attention have some transformation that requires the values that might shoot over the a particular range. So in order to limit the range and proper calculation of attention, the input feature maps or the values inside the feature map have to be normalized. So layer normalization is nothing but only that. So suppose we have the various neurons x coming as a vector here, x coming as a vector here. So the the mean of this layer, the mean of this input layer mu, and a particular input xi is subtracted and divided by the standard deviation. So this is nothing but the layer normalization. Uh, there are several other variants of this layer normalization, like group normalization, uh, and many other methods or many variants that one can try for specific applications, right? So the swing transformer layer is simply that. So one may ask, what is the difference between this layer normalization come attention? Means this is a transformer block only. So what is the difference between this simple transformer and the swing transformer? Okay. So let me describe that. So in the swing transformer block, the patches. Let me clear this. Okay. In the simple transformer, we have the patches embedding, and based on that, the calculation will be done. But in case of swing transformer, there is a concept of windowing. Okay, so this is window 1, this is window 2, and suppose we have another patch, so this is window 3. Okay, and window size, just as a simple case of sliding window protocol in the networks, computer network, these window may contain more than one patches, right? And while calculating the attention score, uh, suppose we have a patch, right? And patch division is such that some person is clipped in half. This is patch 1 and this is patch 2. A person is clipped into half. So while calculating the attention score, one may not have idea, or while calculating attention score on P1, one might not have any idea about the P2. So windowing is simply considering not a single patch but a series of patches for better context, right? So suppose a single window contains more than one or two patches, or simply contains two patches, then at least in one of the window, these two patches will come together. And in that case, the attention calculation or the image reconstruction or any other important calculation will be seeing part of P1 and P2, means seeing the entire man's image, right? So as to provide the better context, right? So this is the difference between the swing transformer and the normal transformer. Swing means shifted window. So there will be a series of window, and each time the window will be shifted by the window size, and there might be some overlapping patches in adjacent windows for better understanding of the context. So this way, modern swing transformer, yeah, or modern or the recent models have not abandoned the swing transformer layer. In fact, added more kind of attention, but kept the basic swing transformer as a basic building block. Right. So when we have defined the swing block, let's define the swing transformer block. Okay, so what swing transformer have is it consists of several swing blocks. If you have gone through the paper of original swing transformer, these these are basically swing block is the main key transformer block, and since it has been designed using the class means object oriented programming, thus main transformer block or main key block may have any number of swing block inside it, right? So let's see that only. So swing transformer have the patch embedding, clear, then have one swing block, right? Then have another swing block. So swing block has been defined here, right? The swing block has been defined here, right? And we may have any number of swing block as we desire. So for simplicity, I have chosen only two swing blocks, right? And then we also have the channel attention block, and the number of channels, number of input channel has been taken into 64, right? Then after that, okay, since it's a classification problem, let me just show what a classification problem is. So classification problem for any CNN based architecture will be giving some image, right? And and the model will classify into, suppose we have a binary classification problem, so model will classify this image into one of the input output classes 0 or 1. If we have more than binary classification, so more label can be added and more number of classes might be there. So that is called multi-level or multi-class classification. So what a multi-class classification is, swing transformer never reduces the image size, right? Image size means the image which will be fed into the swing transformer block, some attention will be calculated and the image is passed to next one, right? But we need our suppose we have 128 cross 128 image. So, and suppose we have a binary classification. So the output, so input is 128 cross 128 image, and output must be one of the output classes, means either 0 or 1. So this image have to be passed in the model, and the model should output only 0 or 1 based on the vector of probabilities, right? So in order to do that, this image have to be transformed into a vector of probabilities, and the cardinality will be 2 only. So suppose it outputs 0.67 and 0.33. So based on that, we'll say that the probability of being this image belonging to class 0 is 0.67 and belonging to class 1 is 0.33. So this image may be, based on probability, be assigned class 0, right? But the important part is every image have to be converted into this vector. So what are we doing to reduce the dimensionality or the size of the feature map? So this is done by using pooling. Okay, pooling. So you might have seen there is a pooling in the channel attention as well, and finally a kind of pooling in the transformer block as well. Okay, so transformer block, the pooling present in the transformer block right here will reduce the image after each block, and finally be assigning class levels, means by reducing the dimensional of the feature maps. Okay. And after pooling, we have finally a fully connected layer of where the softmax function or any classifier function can be used. So our model has been trained while we were describing the model. Okay. So in the training part, so when we have okay, so here we have CUDA, since some computing time and resources were left. So I have selected CUDA. If you don't have CUDA available, you might go for CPU as well. But CPU will take more time. Just at the morning lecture, you might have seen that the GPU are the key instrument of training these kind of heavy models, right? So when CUDA is not available, you may choose your own laptops if there is a lighter model to train. Otherwise, we'll have to acquire computing resources. And finally, we have defined our model swing transformer, and will put we will transform this model to the device, and device contains what? CUDA, if CUDA is available, else CPU. So this device will have either CUDA or CPU based on this statement. If CUDA is available, then CUDA, otherwise CPU. And when our model is has been defined, we will move our model to the device. One thing should be noted that uh, when we have model on a particular device, maybe GPU or CPU, the data set should be or data loader must be moved to the same CPU, means same device, if CPU or GPU. Okay. Then we'll train the model, and the training result are already available here. Okay, so we will analyze and plot the necessary graphs later. So in doing so, we need a criteria. So criteria is what? The two key one key thing is cross entropy loss. We have used this is an MNIST data set example. So I have already described the data set, means 0 to 9 digits. So the input will be a 128 cross 128 image, and output is one of the digit, means 0 to 9, means 10 classes. So output have 10 classes. Okay. So for that, in order to train that model, the criteria is cross entropy loss. That is basic of any classification problem. And we have an ADAM optimizer with learning rate 0.001. So maybe I assume most of you will be would be familiar with the basic machine learning terminologies. If not, so our goal is the machine learning model reduce the losses such that by differentiating the loss function, differentiating the loss function, which is described by L theta, where theta is parameters, and loss function is differentiated against the parameters such that, and we need to find out a point where the loss is minimal, and corresponding to that point, what are the values for parameters, different parameters, theta 1, theta 2, theta 3. Okay, so that value will be considered. And learning rate is, it is the step size. So learning rate is, suppose we have initially there will be more jump towards the accurate result, so that is fine. But if we keep the learning rate 1 or 2 high, the same step size will surpass this optimal value. So for better understanding and better learning, the learning rate should be as minimal. And this is a hyperparameter, means the user or the model designer or the implementation or the person responsible for the implementation has to select these values. Now, so here we have train losses and test accuracies as a function which will be used. Sure, sir. Sure, sir. I'll be sharing this. Yeah, I'll be sharing this notebook file. Also, I will share whatever the GitHub repos we and the various speakers might have. And we'll also share the email ID if someone wants to connect with us and maybe some collaborative project. We'll be more happy. We'll be more happy to do it. Thank you, sir. Okay. And now we have the number of epochs type. As I said earlier, the limitation of the GPU for demonstration purpose, we just kept it the number of epochs as 5. Also, uh, there is a basic terminology which I believe most of you will be aware. Suppose we have a series of data and we pass one data point at a time, and based on that, based on this data, this is the data. Based on one point of data, when available, we can change the model parameter by seeing one record at a time. Then this is called, if someone know the answer, may message. if we are changing the model parameter just by seeing one data record at a time, then this is called stochastic gradient descent method. If we have seen or compiled all the data, we have fed all the data to the model and updating the model parameter only at the end, then it also makes no sense. And if we are updating the model parameter after seeing each data record, that also makes no sense, because that requires a lot of computation. However, there is a more decent approaches. We we divide this data into multiple batches. Okay, so after completion of each batch, which may require some portion of the data, okay, so suppose we have 1,000 total data, 1,000 images, and we have 10 batches, then each batches will have how much? 100 images. So that number of batches into 100 images in one batches will give you the 1,000 images. Okay, so after completing one batch, we will update the model parameter. In this way, we will have more information while training the model. We'll have more accurate information that how well the training is going on. All right. And a simple run will be over the epochs or number of epochs, where the model dot train is called. Model dot train, what does it do is it feed the data. It feed the data that has been present in the data loader. If you can see here, it will feed the train data in the to the model by using the model train. And what role these images and labels. So image, so for a classification problem, what our goal is, we give an what the input is having, this we are having 0, so the label should be 0. MNIST data set. If we have 9 in the image, then our label should be 9. Okay, so these are nothing but images and labels in the train loader, if you can recall it. And these have to be brought to the device on where the model has already been residing. If you can recall, as I earlier said, the data set and the model must be on the same device. Okay, so device we have already defined above. And now this input images and the corresponding labels have to be brought there, right? And in each iteration, this input image will be fed to the model. Okay, and the corresponding level, the model is there. This input image is fed here, and one we have true label. Okay, when we have true label, that is defined using these labels, and something the model will also pick up, something the model will also during the training where the parameters are not stabilized yet, it will give you some output level. So suppose when it will give you 4, then we have the perfect training. If it will give you 9, then according to 4, these model parameters have to be adjusted in the back propagation. Okay, and for that we have selected the output, and we'll calculate the loss based on the output, means what the model is predicting, and the label, the actual label which is associated with the input. If there is any difference in these two values, then we will differentiate the loss. We'll differentiate the loss using backward. This is the back propagation. Okay, this is the back propagation. What I earlier described, that when there is a loss, means the output or the corresponding input layer are different. It means the model is not giving you the correct answer, and for that the model should adjust its parameters, right? And based on that, the optimizer will be the optimizer dot step method will be called. Optimizer adjusting its values. Okay, and this running loss will be added into an item. What is item is, we are storing these losses as items, and will be use this variable to plot the loss at the very end. Okay, now the average loss will be means after the training is complete, and the loss means after a particular pass, the average loss of this particular epoch will be calculated as the running losses and the length of data loader, means the entire loss what has been defined in an epoch, and the total iteration in particular epoch. Okay, then the division is performed and average loss is returned here, right? Okay, and finally this loss will be appended in a uh, means appended in a vector. Why it is appended, we'll show that. And finally, the model is evaluated for its accuracy. Okay, so for that we have some testing images, right? So for testing, the parameters should not be, while testing the model the input is provided simply, and the output and the required level will be seen. So for this testing, the model is there will be no differentiation of parameters, means the parameter should not be adjusted during the testing. For that, we have used with torch.nograd. What does it means is, we have called the library torch.nograd. Nograd means no gradient, means no differentiation for this part. And for this, what we are doing, this is very similar to the training part, and we have used test loader. If you can see here, we have used the test loader here, and again the test images and labels have been put into the devices where the model is residing, and we are calculating the output here. Okay, and now uh, we are using the we are using the probabilities and max prediction. So we have with us the predicted values and the correct values. Okay, and now we can use these to calculate the exact percentage of values, right? And finally, at the end, we are printing what? The epoch number, which is 0 to n, right? So 0 means indexing. So we for 0 to be represented as epoch 1, we are just using the +1 here, and dash number of epochs. So number of epoch is 5. Okay, and then the loss values. Loss value is represented in 4 significant digits, and then test accuracies, that too after decimal 2 significant digits. So we can see that these values are being represented while the training, right? So after training, we are plotting the plot accuracies. So what we have here, let's plot that. Okay, so we have some losses going down and test accuracies going up, means the model is somewhat performing better, right? But how better, and what improvement can be done, that we'll be discussing later. Okay, so we have used figure size subplot, means plotting the same I mean two images in a same figure plot. So we are using subplot here. So subplot 1 means one subplot, and index 2 1 and 2 2, right? So the epochs loss and training loss has been plotted into, means training loss has been plotted into the first figure, and the test accuracy has been plotted in the second, and that too epoch by epoch. So that data that I described earlier is where is it is yeah, train losses and test accuracies that we already have, and the range means 1 to number of epochs +1, means 1 to 5 or 0 to 4, that we can say, has been used, and corresponding train losses and test accuracies has been plotted here. Okay, and now since we have the data with us in the test loader file, so just iterate over some of the data, let's take some of the data, and try to use our model to predict the actual class levels, and let's see how well our model is behaving here. So we use model.eval, and for that, these images again have to be brought into the device. Let's be careful, very careful here. I'm repeating this again. When you have the model on one device and data on another device, it will create problem. Okay, it might show some throw some error that data set is not present or a wrong device, something like that. So be very careful. The data set and the model have to be present on the same device, whether it's GPU or CPU, right? And these data, these labels and images will be again placed into the model, and the output will be calculated. Now we'll again use dot.max to corresponding to the maximum probabilities, and plot the images, and then predicting its actual class level and its output, right? So let me run this again. Okay, so now we see that there is change in some images. So we can see that this particular image 7 is very clear, and it should be predicted as 7 number, so that is good. The second image is 2 according to us, but model is predicting this as 5, means wrong. Again, the next prediction is 1, and the actual image seems to be 1 also. So it is represented in green. You can choose any, I mean, color scheme or any other way to plot these kind of results, right? So again, the prediction for 0 and 4, 1, 4. So most of the values are correct. Let me run this again and show some other results if possible. Yeah, it's repeating itself again. Yeah. So the same set of images has been selected here. Okay. Now let's have some more inference. Inference means some more inference means passing the more of the test data and recalculating it. Okay. So again, we can see that most of the values corresponding to the accuracy of 86.44 means most of the values, or 86% of the values are mostly correct, means we are getting the correct prediction for that. So I will be sharing the notebook file for this particular problem that I have already with me. And again, let's have a very quick uh, scheme of graph neural network that I have selected. So I believe this has taken most of your precious time. So I'll be just doing a, yeah. Okay. So I'll be doing this very quickly. So so we'll be importing necessary libraries, and we have not used images, but randomly generated 100 sample of data sets with 10 node and 5 input features. Means it will be like this. There are 1,000 values total. Okay, 10 nodes and 5 input features, means this part is 5. So any data frame kind of example can be considered for this, and this is for graph neural network or graph convolutional neural network. So we are generating data, any random data for this. If we had some more time, I might have uses the images for this example as well. Okay, so what is graph convolution layer and how it is different from the traditional convolutional neural network is, in this traditional convolutional neural network, what we have is one particular layer is connected with another layer only. Okay, and there is no connection between this, okay, between this and this. So what is a graph convolutional neural network is, in very generic sense, it have some graph, maybe sparse or dense graph. and these nodes are connected in any way possible, like a general graph, not like multi-stage graph as the convolutional neural network. And when the input is passed, some of the node will act as receptors, and finally some of the nodes will act as output, and based on that the output will be computed. So, if possible, I'll be sharing some more example on this graph neural network, and maybe some papers that one of our research team has done here at the end of this FDP. Okay. And then we define a simple graph convolutional layer. I am not going much into the detail. I'm just sharing this is a graph convolutional neural network, and there are some self loops. As we know that there is no self loop in CNN network, but as a general graph, the self loop might be present. Okay, so we are using the self loops, parallel edges, or any other concept that the general graph provides, and not the multi-stage graph. Okay, so that model has been defined here, and now we'll use this convolutional features to define a simple GCN network that uses these two convolutional neural network. Okay, and then using a global average pooling. Okay, and now we use that synthetic data set that we have already defined here. Use that synthetic data and load this using the data loader. So data loader is a key component while loading the data to the device and then feeding it to the model. And finally, we'll initialize the model, loss, and optimizer. Okay, for here I have selected 50 for number of epochs, and most of the code will be very similar. Our training code will be very much similar to just we have just seen the swing transformer based classification problem. And here we see the losses and accuracy. So you can see that accuracy is improving a little bit, and losses are going down. But it is very visible that for to improve more accuracy, maybe we just need more complex model, or we need to run for a more number of epochs. And finally, we'll be plotting using this trained data. We'll be plotting the graph. So the accuracy curve in blue line, and the loss curve has been shown in green line. So the loss is going down over the epochs, and the accuracy is keep improving. So for more improvement, we can either have a more complex data set, more complex model, GCN having more layers, or alternate, we can improve or we can increase the number of epochs to test for more accuracy. And finally, we have some data and try to predict its classes. So since the computing resources were limited, so I have not used images in this. Maybe at the end of FDP or before in the end of FDPs, I might be sharing some more GitHub links for you to try. So if anyone have any question, please don't hesitate to ask.
Okay, okay. Thank you, Dr. Naveen Tiwari. It was very informative lab session. So participants, if you have any questions, raise your hand or just type in the chat box. Anyone? Any questions? Okay, so thank you, Dr. Naveen Tiwari, once again.
Thank you to all the participants, and we'll be meeting tomorrow. We'll reconvene at 10:30 tomorrow. I'll be sharing the necessary and required resources in the WhatsApp group.